And we are now on T. We will resume half past the hour at 3:30 UK time. How's the room looking? All right, it's my pleasure. Welcome back, everyone. It's my pleasure to next introduce Sergey Fomin, who will be speaking to us about Heronian Friezes.
Hello, everybody. Many thanks to the organizers for this invitation. It's great to be back at the Newton Institute, where I believe the first talk about cluster algebras took place in 2001, I think, by Andrei. And I can't wait to join the program in person in 3 weeks' time. This is joint work with Linus Setiabrata, who is now a graduate student at University of Chicago, capital U. So it's been published in IMRN already. So what is this about? Many generalizations of the cluster framework have been suggested over time. I won't list them all. Common to all these variations is the following feature, that algebraic mutations are always birational maps. So we can go forward and backwards just using some rational function formulas between two adjacent cluster charts. So the question I'm going to ask today is there some reasonable version of this framework in which we don't have birationality? What do I mean by this? So let's say this is your exchange relation, and so you are switching the variable xk for the variable xk prime, and there is some equation that relates them, right? So what if this equation is not linear in xk prime, right? So some algebraic equation, right? The exchange relation, of course, is linear. Xk prime doesn't appear, squared or cubed in that equation, right? And that's why it has a unique solution. So if this is, let's say, a quadratic equation, then there are two solutions. How do we know which one to choose, right? It seems to ruin everything. And I will try to argue that it doesn't ruin everything, that there must be some kind of more general setup in which even more general algebraic maps that, generally speaking, ramify could play a role. So what's the plan for today? So I will focus on the cases where we at least know the underlying combinatorics. So type A, this is something that we all know, very well understand. The combinatorics is governed by triangulations of a polygon. So that should hopefully serve as a guiding principle for us to choose the branches of our algebraic maps that somehow will be the right ones. And I'll try to make sense of this, right? So we need some additional combinatorial information to make those decisions. So like I said, the combinatorics will be familiar, so which doesn't mean that it will always be the same in some future theory that somebody will develop. I have no idea what that general theory will be, but even in this case that I will present today, the algebra will be quite unusual. So a very quick reminder for those of you who are not experts in cluster algebras, and I don't think there are any, so it will really be very fast. So in type A, everything is governed by the combinatorics of triangulations of a convex polygon and flips in them. And a particular kind of elementary instance of this is the Frieze patterns introduced by Coxeter which are tables of numbers in which, you know, the red entries here are fixed. These are the initial data, and then you propagate to the right using the condition. Then in each diamond like this, you know, the determinant of this 2 by 2 matrix is equal to 1. So there is a vast literature on this, and a great survey by Sophie I recommend to everybody. So that's these are the usual Coxeter-Conway Frieze patterns. And what are the main results? Well, first of all, these things amazingly turn out to be periodic. Moreover, every entry in a frieze it turns out to be a Laurent polynomial in the initial data, a priori rational function, but turns out to be Laurent actually with positive coefficients. This is an illustration of this phenomenon. Okay, I assume everybody knows this. And why is that? Like, how do you explain all of these things? Well, oh, sorry, before we even do that, there is even something better than periodicity, something called glide symmetry. So the pattern that you see here gets reproduced in a upside down fashion within this triangle, and then again upside down here, and which is a shift of the original triangle. And so you get this kind of parallelogram shifted. This is, so you get periodicity, but you get even something better, which is called glide symmetry. Okay, so why do we have this? Well, like I said, it can be explained via triangulation. So we can represent the initial data using this picture, and then they get evolved using these relations that I mentioned, the SL2 relations, which become the Ptolemy relation. And so we compute f and g, and then the same way we compute g, h, I, and so forth and so on. And this keeps rotating until we finally arrive at the same triangulation with a different labeling, and we recover A, B, C, D. Okay, so this is the story that all of you, I imagine, know very well. Now, there is a version of this story, just to generalize just a little bit, where we introduce coefficients. So remember, here, all the variables associated with the sides are set equal to 1 in the Coxeter setting. But there is no reason to do that. You can put some other numbers. And this translates into associating some parameters, which are coefficients in the cluster setup, to these dashed lines that you see in this frieze. And what is the role of these dashed lines? Well, each time we're doing a flip in a triangulation, which corresponds to going from these 3 entries, you know, to the 4th value in the frieze, right? We are dealing with, you know, 1, 2, 3, 4 with these 4 diagonals, but then there are also these 2 boundary guys, and these 2 boundary guys are encoded by the 2 dashed lines that cross the corresponding diamond. So these are the 6 parameters, the 6, you know, 4 choose 2 line segments that connect these 4 points. They correspond to the 4 vertices of a diamond and the 2 dashed lines that cross it. Okay, so this is also will be part of the boundary data for the Frieze pattern with coefficients. You can easily figure out the rules for this. And of course, the glide symmetry also holds in this setting. Now, the explanation for this, for all these phenomena, come from cluster theory together with the interpretation of these things as geometric quantities. So we interpret them as certain lambda lengths, and they satisfy Ptolemy relations. So this provides intrinsic interpretation to each entry in the frieze or each diagonal, the variable associated to it. And so then we interpret each cluster pattern using, triangulation of an ideal hyperbolic polygon decorated with oracycles and so forth. So there is this story, which is a little bit too complicated because you have to know hyperbolic geometry for that, which seems a little bit like an overkill for such an elementary thing as these friezes, but it is what it is. Now, one can ask, what if we don't go into hyperbolic geometry, just try and do it all on the Euclidean plane? What's wrong with that? Let's just take a convex polygon or some other polygon and triangulate it. It's easy to define what that means, and then do the flips and so forth. So what's not going to work? So what's wrong with the usual Ptolemy relation? In other words, we know EF equals AC plus BD. This is Ptolemy's theorem. Well, it requires the quadrilateral to be inscribed into a circle. Okay, fine. So what's wrong with that? Well, for the inscribed quadrilateral, A, B, C, D, E are not algebraically independent anymore because this triangle BCE and this triangle ADE, they should have the same what is it called? This circumcircle. The circle going around this triangle and the circle going around this triangle should be the same. So this gives you an equation. And we don't want that. We want ABCDE to be algebraically independent, and then we will transition to F. Okay, so this doesn't work. So what does work on the plane then, you may ask? Well, let's just drop this requirement for the polygon to be inscribed, right? Then there is some other equation, right? Because if there weren't, then we wouldn't have the previous phenomenon. What is that equation? This is the Cayley-Menger equation. So these 6 distances, they satisfy a certain equation which expresses the fact that the volume of the tetrahedron with edge lengths square root of A, square root of B, square root of C, square root of D, square root of E, square root of F is 0. Okay, so here A, B, C, D, E, F are the square distances, which is actually good because square distances make sense even over complex numbers, right? Whereas the distance, is square root of something, and then like which square root do you take? So we encounter the problem that I already mentioned, right? But so this equation involves only square distances, which makes sense. They're regular functions, so we just uniquely define. So looks good. We have an equation. So let's work over the complex numbers from now on. A2 will be my notation for the complex plane endowed with a Euclidean structure. So there is a bilinear form, and there is a you can shift things. Just the usual setup. So we can introduce these Cayley-Menger friezes now. If you know 3 entries here, you find the 4th entry, together with, of course, you also need to know these 2 parameters from the boundary. In this case, the boundary is all 1s, so it's the usual sort of without coefficients, with trivial coefficients, friezes with trivial coefficients, by Cayley-Menger friezes, right? So we want the Cayley-Menger equation instead of the Ptolemy equation. Okay. Unfortunately, there is a problem. The Cayley-Menger equation is quadratic in F. That's the thing that I discussed on the first slide, right? Because F appears here twice. So when you write out this determinant, there will be a term with F squared. So because of this, the exchange map is not well defined. We have 2 different values of F, and like which of the 2 do we need to take? Of course, on the plane, if it's convex, you can sort of see which of the 2 solutions we need to take, but of the complex numbers, like it's not clear. And well, this phenomenon has a very simple geometric explanation. When you fix A, B, C, D, E, there are actually 2 pictures that you can draw, right? You can flip this triangle this triangle, you can flip over this edge E up, bottom up. And then you have this picture on the right. And of course, the values of F are different in the first picture and in the second. These are the two roots of the Cayley-Menger equation, okay? So how do we know which of the two roots to take? Well, it looks like it's kind of bad, but it's not so bad, right? Because if we choose the right branch among the two, right? Then let's say in the case of real things happening on the plane, one of the choices will give us periodicity. It is subject to some Galois theoretic choices that we have to make in advance, but it's easy to convince yourself that even over the complex numbers, if we do this flip and choose the right branch, and then this flip again choose the right branch, like take analytic continuation in the vicinity of the right choice for the complex, for the real picture that you see on the screen, right? So then, there will be like 2 to the 5, 32 different ways to play this game, but one of them will terminate in exactly the same seed as we started with, right? So if somehow we can throw in some additional combinatorial data, somehow change our game to be a little more sophisticated so that it would account for this right choice of branches, then we will come back to the original values, right?
Sergey, excuse me. How do you know that it's only one choice?
Oh, maybe not one, maybe more. Yeah. Anyway, whatever works, right? And some of these 32 will give you the same things. But we know that there is at least one way to play this game that will be consistent. So, like how to play. The question is how to play the game, right? What?
So you don't claim that it is only one choice. You say that choose.
No, I don't claim.
Okay.
I don't claim that. I believe that's true, but I don't claim that. Yeah. So so that's the question, and there are two ways to answer it, which I will present if I have enough time. If I don't have enough time, I will only present one, and then you will ask me what's the other at the end. So the idea is that we expand the measurement data. In addition to the squared lengths of the sides, we will also record the signed area. Okay, so S is the area. I want to normalize it by a factor of 4. Not important. So I want the area. And there are, of course, 2 different values for the area, right? Which differ by sign. So this is essentially a combinatorial choice, right? But I want to make that choice because you can flip this triangle over and the distances will still be the same, but the area will be different, right? And it's easy to believe that a triangulated polygon is uniquely defined by the collection of all measurements, by which I mean the square distances of the segments forming the triangulation together with the signed areas. Of course, the signed areas have to satisfy Heron's formula, right? This is the formula, which is almost 2,000 years old. And you may wonder what these square roots are. Remember that A, B, C are square distances. So you need to take the square root of A, B, and C in order to write the formula in the form that all of you learned in high school. But of course, we don't need square roots. Square root would be verboten in the complex numbers. But when you expand this, you just get an expression without square roots. So and this is well defined over complex numbers. So this is Heron's formula, and this is true also over complex numbers, right? Of course, if it's true over the reals and there are no square roots, it should be true over complex numbers. And conversely, if you have a bunch of A, B, C, and S, 4 numbers that satisfy this equation, not all of them equal to 0, then there exists a triangle with these measurements, and moreover, it's unique up to the automorphisms of this Euclidean complex plane. So let's now think about the flip. So what happens here? Well, So before the flip on the left, after the flip on the right, Heron's formulas should be satisfied. Are there any other relations? There must be other relations, right? Because once we know these guys, we know the picture on the left. So this should uniquely determine the stuff on the right. And so, like, how do we find the stuff on the right? That's the question. Okay. And one equation is easy to guess. The area on the right, of the quadrilateral is the same as on the left. R plus S equals P plus Q. The others are much harder to figure out. This is one which we couldn't find in the literature, but we discovered it nevertheless. It's a pretty tricky relation. It doesn't look symmetric at all. It's kind of a bilinear. It's separately linear in the areas and linear in the squared distances. Anyway, it's true. And it's true. And notice this equation is linear in R and S, just like the first one. So we have two equations in R and S. From these two equations, you can find R and S uniquely. Okay? And there is another beautiful formula called Brett-Schneider's formula from 19th century geometry, which is almost like the exchange relation. E times F is equal something. Something, well, P plus Q is the area of the quadrilateral squared plus this strange thing, square of the alternating sum. And remember, A, B, C, D are squared distances, not the lengths, but the squared lengths. Anyway, this is true. Okay, so from here we find F. So now we have exchange relations, right? This shouldn't be surprising because these parameters are uniquely defined by the left parameters, right? Since they are defined uniquely, the formulas have to be rational, right? And they cannot ramify. But you may wonder, oh, we started with something that satisfied Heron's relations, right? So these were not algebraically independent. We have A, B, C, D, E, which are basically arbitrary. There is no triangle inequality or anything like that, complex numbers. But then we have P and Q, which are like some square roots of the Heron expression, right? They satisfy Heron. And then we define R, S, and F by this formula, right? But who said that R, S, and F will satisfy, together with A, B, C, D, the Heron relations on the right? But of course they do, okay? Because the world is beautiful, and so, and the Heron relations propagate. All right, so now we have everything in place. So what does this give us in the Frieze world? Well, we have to add these signed areas somehow. And it turns out that the right place for them to live is in the at the midpoints of these edges, right? So each of these two edges, these 2 points corresponds to a diagonal in the quadrilateral. These are adjacent diagonals, so to speak, like this, right? And there is a triangle here, and the area of that triangle will be sitting here, okay? So that's the rule. And so now we are going to propagate and get values like this. So how does it work? So we know these three values, right? And also the 2 crossing ones. These are the 5 A, B, C, D, E. And we also know these 2 areas here. And this uniquely defines this guy, and this guy. Okay? So again, you start with some kind of, maybe this line, right? This is all, these are the initial conditions. And you also know everything which is dashed. And then this uniquely defines these 3 guys by the formulas that I just showed you. And then these 3 guys, and then these 3 guys, and then you just propagate to the right. Okay? So that's the Heronian frieze. And it turns out that any such frieze, it's not hard to believe, comes from an actual polygon. And since it comes from an actual polygon, it has the glide symmetry. And in fact, not just the glide symmetry, you can build the entire cluster complex, and everything will fit together in exactly the same way as before, except there will be all these extra adornments. You know, each cluster will also be accompanied by a choice. You know, one of the, you know, by like things which come from choosing one of the two square roots for certain expressions, right? So this will be this extra kind of combinatorial, Galois combinatorial information that will enable us to propagate uniquely. And lo and behold, the Laurent phenomenon also holds. In fact, everything will be Laurent with respect to the initial cluster. So initial cluster is here shown in black, and some distant measurements are shown in green. So these two squared lengths will be written, you know, as Laurent expressions in the initial data, and moreover, the area of this green triangle will also be expressed as a Laurent expression. And in the denominator, we will only have squared lengths of diagonals. So these signed areas, they won't appear because they are just combinatorial information. We're not supposed to, they're sort of not as algebraic as the rest. Okay, so that's the end of the story about Heronian friezes. And now, okay, I have time. So let me tell you another way of handling this issue. So that alternative way has to do with the idea of introducing bracing edges. So here, if you only know all these distances, right, then you can sort of bend your, right, if you just glued these triangles to each other along these diagonals, right, then you can flip over your construction, you know, flip over each of these edges, right? So in order to freeze it in place, make it rigid, one way to do it was, as I said, introduce signed areas, but there is another way, which is introduce these bracing edges, right? Some extra values, which are of course almost uniquely defined, you know, up to a choice of a root of a quadratic equation, as we discussed, right? But once you drew these green things, these quadrilaterals, this one and this one and this one, they are now uniquely defined, right? We cannot do the bending along their diagonals, right? But this is still not frozen, not rigid, because you can bend with respect to this diagonal. So we need a couple of extra bracing edges, and now everything is fixed, right? So this is another way to introduce this extra Galois theoretic information to make things rigid, and then things will hopefully propagate birationally. Okay, so how do we do this explicitly? So, okay, this is a reminder of what the Cayley-Menger polynomial is, which is supposed to be 0 when these 6 numbers are the distances, square distances between 4 points in the plane. I will also need the derivative of this polynomial, let's say with respect to the last variable f. And I denote this by q. All right. So it turns out that if you take 4 sextuples that are indexed by 1, 2, 4, 5, 1, 2, 5, 6, and so forth. So who are these guys? They are, so we take 1, 2, 3 here, and we take 4, 5, 6 here, right? These are the guys that will appear in the frieze. And then I want to take this quadrilateral, but also this quadrilateral and this quadrilateral. Okay? And so I want, for each of these quadrilaterals, I write the Cayley-Menger equation. It should be satisfied by these guys. And it's not hard to show, like using some Grosvenor basis package or whatever, that this identity holds, that it is in the ideal generated by these Cayley-Menger polynomials. But it turns out that you cannot remove the squares here. Okay, if you remove the squares, it won't be in the ideal. But if the picture comes from actual 6 points, then there is some extra information coming from rigidity. And that extra information forces this identity without the square. Okay? So we know which of the two components of this reducible variety we need to take. Like the squares, you know, are equal when things are equal, or one is minus the other. And we want the plus option. And that is fixed by you know, deciding that we want this extra condition, which is really not an extra equation. It doesn't bring the dimension down. It just picks the right component of a reducible algebraic variety. So we call this condition the coherence condition. So now our Cayley-Menger Frieze is called coherent if whenever you take 4 diamonds, which are all next to each other, and they correspond to those 4 quadrilaterals that I showed you on the previous slide, the corresponding data will satisfy the coherence condition. Okay, so we want this equation. The square equals square equation already is automatic just from the Cayley-Menger condition, but we want more. We want the things to be equal to each other. Okay, and then we have a Cayley-Menger Frieze. And now the beautiful thing that happens is that that coherence condition has degree 1 with respect to the guy on the right. So let's say we know this guy, 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 this guy. We know all of them, and we know all the information that comes, you know, from the boundary of our polygon. Okay, so all of this is known, and the question is, who is this guy? Right? Well, you just write that coherence condition, and the coherence condition turns out to be not quadratic but linear in this variable, so it will be uniquely defined. Okay, so what does this mean in practical terms? It means that if we start by fixing, in addition to our usual, you know, initial data for the frieze, some choices for the next layer, right? So how do I find this guy? Well, from the Cayley-Menger equation, just pick any solution. There are 2 solutions for the Cayley-Menger equation for this diamond. Pick any of them, doesn't matter. And then pick any solution here. And of course, this one is on the boundary, okay? But that's it. Now you don't have any freedom. Now you propagate to the right. You have a thick crosscut, and this thick crosscut. Oh, sorry, no, sorry. We also need to choose. I'm sorry, I got too excited. We also need to choose these ones again in an arbitrary way, right? Because we want like duplicate the initial data. Okay, and now we are ready to propagate because we have these 8 guys, and they uniquely determine the ninth one. Okay, so starting from here, there is a unique propagation to the right because we resolved the ambiguity. We kind of rationalized our recurrence in the sense of making it rational as opposed to quadratic, you know, having to solve the quadratic equation. And now everything works, and we get a frieze which actually generically comes from a polygon. Therefore, it has glide symmetry, and in fact, you can build the entire cluster pattern, which again will have all the properties that we like. And so, what does it mean in cluster terms? It means that somehow we started with a cluster. We didn't know how to mutate away from it because there were choices. Let's make arbitrary choices for just mutating once, right? And then propagating beyond that becomes unique by this extra Galois theoretic information. I'm not sure how to encode it in general in a setting which is not type A. You know, this is kind of a case in point that such things exist. I don't know what the general theory is. It would be great to figure this out. Okay, that's all. Thank you.
Thank you, Sergey. As usual, I'll start with questions in the room.
There's a question here. Just a moment.
Thanks for the lovely talk, Sergey. Can you say what collections of data you would be enough for you to be able to continue rationally? I mean, you have these two strips gives you enough that you can then continue rationally to everybody else.
Right.
Is what's enough in general?
Yeah, well, that's exactly what I would like to know. Yeah. Yeah, I don't have a general answer because it's not even clear like what the question means, because I need to know what sort of exchange equation or exchange relations I need to consider. Right here we have some kind of a guiding, you know, example coming from geometry. I wish, you know, we are working on extending this in kind of the obvious directions, which are like taking, you know, changing the kind of geometry, right? You can take hyperbolic or spherical surfaces and so forth. But this is not going to be the right generality. You want something way more general, right? Just like in the general cluster setup. So kind of what makes this click? I wish I knew. Yeah, I mean, this is the fundamental question. I'm not surprised that you asked it. I wish I knew the answer. Let me know if you figure it out, or we could figure it out together if you have good ideas. Whatever.
Thanks.
There's another question here.
Hi, thanks so much for the talk. So the story, as far as I understood, it's a story about an angon, right? And like mutating diagonals in an angon. Do you think there is any chance to upgrade it to a more general surface?
To a more general surface. Well, do you mean a surface with flat geometry, like a torus, or a surface with like hyperbolic geometry? You know, most surfaces don't allow flat geometries, right?
Sure, but,
so,
but let's say a torus.
Yeah, it should be possible. Yeah, I don't see why not. I mean, it would have to be tweaked in certain ways, but yeah, I don't see any. I mean, it probably won't require any kind of new algebraic ingredients. The ingredients will be the same, meaning like Cayley-Menger will be the same. But of course, in other geometries, Cayley-Menger gets deformed, and there are like, yeah, you get something more complicated, and which doesn't even look algebraic. This is the same problem as the one that Penner faced when he introduced lambda lengths, right? So you want geometric measurements that somehow satisfy some algebraic relations, right? And this requires taking exponentials, and like in the pentagramma mirificum case for the spherical geometry, you know, it was the inside of Gauss that you need to take the squares of tangents of the angles, and they will satisfy you know, the pentagon rule. So maybe something like that will be required. Yeah, but yeah, I don't know exactly. But my feeling is that this would still be too restricted. The general theory somehow should be, you know, more like the theory of cluster algebras, you know, just some some collection of polynomials, some rule for these exchanges, some Galois theoretic data that you know, lets you pick the branches. I don't know what this is going to be. I hope it something exciting. Yeah.
Yes,
Sierra,
Prof
are there
says
other
thank you.
are there other questions in the room?
Doesn't seem to be the case at the moment.
I see a few in the chat, so I'm going to try to get to all of them. But even if you have a couple questions, maybe we'll start with one at a time. So the first question I saw was from Greg Muller, so I'll start there. And then Misha, you'll be next.
Hey, Sergey, as usual, lovely talk. I'm kind of curious, in these cases where you have polygons, if your polygon is cyclic, can you say a little bit about how the Heronian or Cayley-Menger-Frieze specializes and how it might be related to the sort of the classical Coxeter-Frieze that Ptolemy says we should have?
What do you mean cyclic?
Inscribed in a circle.
Ah. Oh, well, that's an awfully restrictive condition.
Sure.
It would, yeah. So basically, we now like drop down to a subvariety of huge codimension, which somehow has the property that, you know, it is invariant under these mutations. So you never leave it. You know, this is like a special. It corresponds to, you know, it's a manifestation of integrability, that you have a certain, you know, a large number of conserved quantities, right? And you can, and so this enables you to mutate, you know, without changing those quantities, and so you remain on that subvariety. So, you know, it's nice to have it, but the general theory, I don't think should kind of worry about these kind of conditions. But it's natural to expect, just from the sort of general integrable systems yoga, that there will be such phenomena, you know, maybe coming from the cyclicity condition or from some other conditions. I don't know.
Misha?
Thanks. Sarah, looks to me, I don't know, on the first glance, like terrible similar to what, well, Greg talked about, like this super Teichmüller, and with more or less the same pictures, like dots and segments, connecting them, and then putting some extra information on these segments, right? And also on Glick and Pilevsky zoo. What is the relation, for example, between this situation and Glick and Pilevsky? So can it be considered a particular case of Glick-Pilevsky zoo?
I doubt it.
Like Y meshes, you know what I'm talking about, right?
Yes, I know. The key difference is that that's a projective theory, right? It's all about sort of cross ratios, and it's about point configurations with certain collinearity condition, right? This theory is, morally speaking, this is all about SO2 invariance, or more generally, maybe SON invariance, you know, special orthogonal group.
Right. Yeah,
and by Weil's theorem, these are generated by squared lengths and signed areas. This is precisely why these guys appear here as measurement data. I somehow doubt. I mean, maybe there is a dictionary between the two. It's possible, but that would mean that somehow, because their story fits into the usual cluster story, right? Whereas
well,
this
sort
one,
of,
yeah, I
but
don't know.
in the
My
method
feeling is
case-
that here we
In-
have kind of different types of data. We have this like algebraic data and then additional Galois theoretic data.
No,
which is also
I think
algebra.
sorry, just in their cases, so in some geometric situation, one can consider also dependence between their variables, which is
Right.
defined by a geometric situation, and then it's propagated,
Yes.
like in your case. You are right that they data,
That's right.
x data, x coordinates, yours are a coordinates.
Yeah, but
But
it's not. Yeah, but I think the difference is that I'm not just looking at some algebraic dependencies which propagate. I am actually explicitly saying, let's just take something which is algebraically independent, but then let's choose by will force certain roots of some equations, right? And there are several choices, discrete number of choices, and we fix a particular choice, and that will be auxiliary data that will let us propagate.
Yeah, but I
This is
think
a little bit.
Yeah, exactly the same thing happens for them if they put like some periodic data on their meshes.
Maybe. Maybe, yeah. I will come to the Newton Institute on December 3rd, so we should discuss it then. Okay.
Oh, okay, sorry, I give up.
No,
I want to.
I mean,
no, sorry, thanks.
No, I think it's a good question. I want to get to James's question next. James, did you want to read it, or do you want me to?
Sure. Hi. Yeah, I was just going to ask about the choices that you make for this extra data. How many choices do you have in general, and do they really give different patterns, or are the different patterns related to each other?
well, again, I don't know. This is a theory in search of, axioms, right? So we are still at the sort of Linnaeus stages before Darwin, right? We are just like before Mendeleev in chemistry, right? We just look at some experimental data. I just wanted to show experimental data that demonstrate that some theory, some writings on the wall, that some theory must exist. And I wanted to present two different versions, right? Because I don't know, like, I don't want to pretend that one of them is the right approach. You could do it this way, or you could do it that way, and maybe there is yet another way. Maybe some of the ones suggested by people who ask me questions. So yeah, I don't know. It's wide open, and I wish I knew. I mean, excellent question. That's precisely what's on my mind. But I don't know the answer.
Thanks.
I don't see any other unresolved questions in the chat. Oh, sorry, another one just came in. Daniel?
Yes. Is it interesting to study other objects in Euclidean geometry and Frieze patterns coming from them, or quadrilateral cases the only one interesting?
Well, there are some. Yeah, I know some other examples. Like there is an interpretation. When I suppose when you say interesting, you mean related to cluster theory, right?
Yes.
Interesting to people in this audience. So I know at least two such examples. One is the Casey's theorem and interpretation of cluster patterns of type A using Casey's theorem about configurations of tangent circles. And another one is what's called the Mikhail dynamics that Kenyon and others studied. So this is like inscribing circles into configurations of circles and things like that, almost like Apollonian game. Yeah.
Okay.
These are the two examples I know, but there may be others.
Thank you.
Other questions, either from Zoom or the room? If not, I think this, oh, go ahead, Melissa.
Yeah, so this is related to other questions people were asking about this extra data. Can you choose the bracing edges to just be another triangulation? In the picture you showed, they crossed each other, but is that necessary?
I don't think this is necessary. I think it's possible, but I would need to. I think it's possible. Yes, I think this is essentially what is happening in this picture on the screen. You know, this is one triangulation, and this is another triangulation.
Right, that's why I asked.
Yeah. I think it's possible. Yeah. Okay.
Great, thanks.
Thanks.
Thank you all for the very nice questions. But I think in the interest of time, at this point, I want to thank Sergey a second time for a very engaging talk. And if it's okay with everyone, I think I'll go with a 4-minute break to put us at 25 after.